Preparing for a GPU infrastructure engineer interview. You've reached Interview Guide, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question, you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a GPU cluster for large-scale machine learning workloads? A GPU cluster is not just nodes with accelerators. It is compute, network, storage, and orchestration working together. I'd start with GPU node SKUs, PCIe NVLink topology, CPU to GPU ratio, memory, local NVMe, and power limits. Then I'd cover Kubernetes or Slurm scheduling, container runtimes, drivers, monitoring, and fast networking like InfiniBand. The key is matching workload patterns. Training needs bandwidth and placement. Inference needs latency, auto-scaling, and isolation. While answering, focus on node hardware, GPU topology, networking, storage, orchestration, scheduler choice, observability, and how training, inference, and batch workloads create different infrastructure requirements. Question 2. What are the main differences between PCIe, NVLink, and InfiniBand in GPU infrastructure? PCIe is the standard host-to-device interconnect, good for general attachment, but lower bandwidth than GPU native links. NVLink connects GPUs directly inside a server, reducing bottlenecks for tensor parallelism and large models. InfiniBand connects servers across the cluster with low latency and RDMA support. In practice, I'd optimize placement so tightly coupled jobs stay on GPUs with NVLink first, then use InfiniBand efficiently across nodes. Make sure to cover where each technology operates, bandwidth and latency differences, GPU to GPU versus node to node communication, and why topology awareness matters for distributed training. Question 3. How does Kubernetes support GPU workloads, and what components are required? Kubernetes treats GPUs as extended resources. I'd install the NVIDIA driver, container toolkit, and device plugin so pods can request resources like nvidia.com/GPU1. Then I'd use node labels, taints, tolerations, and affinity to control placement. For production, I also need DCGM metrics, image compatibility checks, and upgrade procedures. The common mistake is assuming scheduling a GPU is enough. Drivers, runtime, topology, and observability decide reliability. In your answer, talk about NVIDIA device plugin, container runtime configuration, GPU resource requests, node labeling, scheduling constraints, monitoring, and common operational pitfalls in production clusters. Question 4. What is NCCL, and how would you troubleshoot poor distributed training performance? NCCL is NVIDIA's library for high-performance GPU collectives, like all-reduce, broadcast, and reduce scatter. If training is slow, I first compare single-node and multi-node throughput. Then I check GPU utilization, NCCL debug info logs, topology, InfiniBand health, MTU, GDRDMA, and whether traffic falls back to TCP. I'd run NCCL tests to benchmark raw bandwidth. If communication dominates, I tune batch size, gradient accumulation, placement, or communication overlap. Be sure to mention collective communication, all reduce, topology detection, NCCL environment variables, network transport, GPU utilization, logs, bandwidth testing, and distinguishing compute bottlenecks from communication bottlenecks. Question 5. How would you handle GPU sharing and multi-tenancy in a production platform? GPU sharing is useful when jobs underutilize full devices, especially inference and notebooks. I'd evaluate MIG for strong hardware partitioning on supported GPUs, NPS for CUDA process sharing, and scheduler-level time slicing for softer sharing. Then I'd enforce quotas, namespaces, admission controls, and monitoring per tenant. I would not share blindly for large training jobs because memory pressure and noisy neighbors can hurt predictability. Isolation level should match workload criticality. While answering, cover MIG, MPS, time slicing, Kubernetes resource modeling, isolation, fairness, noisy neighbor risks, security boundaries, quota management, and when dedicated GPUs are still preferable. Question 6. What metrics would you monitor for GPU infrastructure health and performance? I monitor GPUs at 3 layers: device, node, and workload. Device metrics include SM utilization, memory utilization, frame buffer usage, temperature, power draw, throttling, ECC errors, and XID errors. Node metrics include CPU, RAM, disk, PCIe, and network health. Workload metrics include queue time, job runtime, failures, and tokens or samples per second. Good alerts catch degradation, not just outages, because slow GPUs silently waste huge amounts of money. Make sure to include GPU utilization, memory usage, temperature, power, ECC errors, XID errors, PCIe throughput, network metrics, job level telemetry, saturation, and alerting strategy. Question 7. How would you investigate a GPU job that is allocated resources but shows low utilization? Low GPU utilization usually means the accelerator is waiting. I'd inspect the training loop with Nsight Systems or PyTorch Profiler, then check data loader workers, CPU saturation, storage latency, network reads, and host-to-device copy time. I'd also review batch size, mixed precision, synchronization barriers, and kernel launch overhead. If utilization improves with synthetic data, the bottleneck is input pipeline. If not, I look at model kernels and memory access patterns. In your answer, talk about data loading, CPU bottlenecks, batch size, memory transfers, kernel occupancy, synchronization points, storage throughput, profiling tools, and application-level instrumentation. Question 8. What is the role of RDMA in GPU clusters, and why does GPUDirect RDMA matter? RDMA lets one machine access another machine's memory with minimal CPU involvement, reducing latency and overhead. GPUDirect RDMA extends that path to GPU memory, so network adapters can move data directly to or from GPU buffers. For distributed training, that matters because gradient exchange becomes faster and less CPU bound. I'd verify NIC placement, PCIe topology, firmware, CUDA, NCCL, and driver compatibility, because one misconfiguration can silently force slower host stage transfers. Be sure to explain remote direct memory access, CPU bypass, network latency, GPU memory transfers, InfiniBand, return on capital employed, driver and firmware dependencies, and benefits for distributed training. Question 9. How would you plan capacity for a GPU platform used by multiple ML teams? I'd start with real usage data: GPU hours, utilization, queue time, job size, memory requirements, and team-level demand. Then I'd classify workloads into interactive, batch training, production inference, and reserved launches. Capacity planning should include headroom, failure domains, hardware lead times, and expected model growth. I'd use quotas and chargeback to avoid artificial demand. The goal is not 100% utilization, it is high utilization without blocking critical work. While answering, focus on demand forecasting, workload classification, utilization data, queue times, quotas, reservations, spot or preemptible capacity, model growth, procurement lead times, and cost controls. Question 10. How do you manage NVIDIA driver, CUDA, and container compatibility across a fleet? Fleet compatibility starts with a clear support matrix. The host driver must support the CUDA runtime used inside containers, so I'd standardize base images and publish approved tags. Upgrades should happen in rings, canary nodes first, then broader rollout after running CUDA samples, NCCL tests, and representative workloads. I'd drain nodes before changes and keep rollback images ready. Uncontrolled driver drift is dangerous because failures appear as random job crashes. Make sure to discuss driver CUDA compatibility, base images, container runtime, upgrade rings, node draining, validation tests, rollback, kernel dependencies, and preventing version drift. Question 11. What causes GPU out-of-memory errors, and how would you help a team resolve them? GPU OOM can come from model parameters, activations, optimizer states, large batches, memory fragmentation, or leaks. I'd first confirm the requested GPU type and available memory, then inspect framework memory summaries and profiler traces. Practical fixes include reducing batch size, using mixed precision, gradient checkpointing, optimizer sharding, or choosing GPUs with more memory. As infra, I can provide visibility and right sizing, but the application team owns model-level memory behavior. In your answer, cover model size, batch size, activations, fragmentation, memory leaks, mixed precision, gradient checkpointing, profiling, allocator behavior, and infrastructure versus code ownership boundaries. Question 12. How would you design scheduling policies for fair and efficient GPU allocation? GPU scheduling has two goals that often conflict: fairness and utilization. I'd use quotas for team-level fairness, priority classes for critical workloads, and reservations for production or launch deadlines. For distributed jobs, I'd support gang scheduling so all required GPUs start together. Topology-aware placement improves performance by keeping jobs on NVLink connected GPUs or same racks. Backfilling smaller jobs can reduce idle time, but preemption policies must be predictable and visible. Be sure to mention bin packing, gang scheduling, priority classes, preemption, quotas, reservations, topology-aware placement, starvation avoidance, backfilling, and trade-offs between fairness and utilization. Question 13. How would you debug a node where GPUs disappear from Kubernetes? I'd start on the node with NVIDIA-SMI to confirm whether the OS sees the GPUs. If that fails, I check DMEG, XID errors, driver modules, PCIe visibility, and recent kernel or driver changes. If NVIDIA SMI works, I inspect the NVIDIA device plugin, kubelet logs, runtime configuration, and allocatable GPU resources. Remediation might be restarting the plugin, cordoning and draining, reloading drivers, or rebooting. I avoid quick fixes that strand running workloads. While answering, focus on device plugin health, kubelet, NVIDIA drivers, NVIDIA SMI, kernel logs, XID errors, container runtime, node labels, taints, and safe remediation steps. Question 14. What is MIG, and when would you use it instead of full GPU allocation? MIG, or multi-instance GPU, partitions a supported NVIDIA GPU into isolated slices with dedicated compute and memory resources. I'd use it for inference, development, or small workloads that need predictable isolation, but not a full GPU. Kubernetes can expose MIG profiles as schedulable resources. The trade-off is reduced flexibility. Partition layouts must be planned, not every workload benefits, and large training jobs often need full GPUs with maximum memory and bandwidth. Make sure to cover multi-instance GPU, hardware partitioning, memory and compute isolation, supported GPU families, inference use cases, Kubernetes integration, limitations, and operational complexity. Question 15. How would you optimize cost in a GPU infrastructure environment? GPU cost optimization starts with visibility. I'd measure allocated versus used GPU hours, idle jobs, queue time, and workload performance per dollar. Then I'd right-size jobs, use cheaper GPU generations where acceptable, enable auto-scaling for inference, and consider spot or preemptible capacity for fault-tolerant batch work. Quotas and chargeback create accountability. I would also watch performance regressions, because a small training slowdown can cost more than a hardware discount saves. In your answer, discuss utilization, right-sizing, idle detection, scheduling efficiency, spot instances, reservations, auto-scaling, mixed hardware pools, chargeback, workload profiling, and avoiding expensive performance regressions. Question 16. What are common failure modes in GPU servers, and how do you design for reliability? GPU servers fail in both obvious and subtle ways. ECC errors, XID faults, overheating, power instability, NIC degradation, driver hangs, or local disk exhaustion. I'd run continuous health checks, collect DCGM metrics, and automatically cordon unhealthy nodes. For jobs, I'd encourage checkpointing so failures become recoverable instead of catastrophic. Hardware failure domains matter too. Spread replicas across racks and power domains. Reliability is a combination of detection, isolation, and fast replacement. Be sure to mention ECC errors, XID faults, thermal throttling, PSU issues, NIC failures, driver hangs, disk pressure, node draining, health checks, redundancy, and automated remediation. Question 17. How do storage and data pipelines affect GPU training performance? Fast GPUs can sit idle if the data pipeline cannot feed them. I'd look at dataset location, file format, small file overhead, preprocessing cost, caching, and read parallelism. Local NVMe caches can help, especially when repeatedly training on the same dataset. For cloud object storage, I'd batch reads and avoid tiny random access patterns. A simple test with synthetic data quickly shows whether storage is the bottleneck. Input starvation is infrastructure waste in disguise. While answering, cover data locality, object storage latency, parallel reads, caching, preprocessing, local NVMe, file formats, data loaders, network throughput, and symptoms of input starvation. Question 18. How would you support production GPU inference differently from model training? Training optimizes throughput over long jobs. Inference optimizes latency, availability, and predictable cost. For inference, I'd focus on model server choice, dynamic batching, warm pools, auto-scaling signals, GPU memory residency, and rollout safety. I'd monitor P50, P95, P99 latency, error rate, queue depth, and tokens per second where relevant. GPU sharing or MIG can improve utilization, but only if it does not violate SLA. Production inference needs deployment discipline, not just accelerators. Make sure to contrast latency versus throughput, autoscaling, batching, model loading, warm-up, isolation, availability, observability, rollout strategy, GPU sharing, and SLA-driven capacity planning. Question 19. How would you perform an incident response for a cluster-wide GPU job failure? I'd first define the blast radius, which jobs, node pools, GPU types, images, or namespaces are affected. Then I'd check recent changes, such as driver rollouts, base image updates, scheduler modifications, or network maintenance. Mitigation comes before perfect root cause. Pause rollouts, cordon bad nodes, revert images, or route jobs to healthy pools. I'd communicate status clearly and preserve logs. After recovery, the post-mortem should produce tests or guardrails that prevent recurrence. In your answer, talk about triage, blast radius, recent changes, scheduler events, driver or image rollouts, network health, communication updates, mitigation, rollback, and post-mortem follow-up. Question 20. How would you benchmark a new GPU instance type before adding it to the platform? I would not approve a GPU type based only on vendor specs. I'd run synthetic tests like CUDA samples, memory bandwidth checks, and NCCL benchmarks. Then run representative training and inference workloads from internal teams. I'd compare throughput, latency, stability, power behavior, failure rates, and cost per successful workload against current fleet baselines. I'd also validate drivers, monitoring, scheduling, and image compatibility. The best GPU is the one that improves real platform outcomes. Be sure to cover synthetic benchmarks, representative workloads, memory bandwidth, interconnect tests, power efficiency, cost per workload, driver validation, stability, and comparing against existing fleet baselines. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.